Right, today we're going to focus on another type of electrochemical cell, electrolytic. These are going to force non-spontaneous redox reactions to occur. So we use electricity in order to force the electrons to flow from the anode to the cathode. We can do this for something called electrolysis, where we're breaking apart compounds using electricity, such as breaking apart sodium chloride or water, and we can also use it for electroplating. So here we want to electrolyze sodium chloride, break it down into solid pure sodium and chlorine gas. So we have our two half reactions. We can see that the chlorine is going to get oxidized, sodium is getting reduced. I've taken these values off of the table that we used in our last concept, making sure that I reverse the sign for the oxidation reaction. So our initial cell potential here is negative 4.07. This negative voltage shows that this reaction is not spontaneous. So if I were to place it in a setup for a voltaic cell, no electrons would move. I need to force it to happen. So here we can see we have our power source that needs to be necessary in an electrolytic cell. What's happening is that our chlorine ions that are in this molten NaCl is attracted to the positive electrode where it's going to undergo oxidation. So one major difference between an electrolytic cell and voltaic cell is that our anode, where our oxidation is occurring, is going to be given a positive sign. So chlorine is getting oxidized, again, at the positive anode, and we actually will see bubbles form as this chlorine gas is produced. Those electrons that are being taken off of the chlorine ions are going to get forced through the wire and arrive at the cathode. Here, the sodium ions, positive, are attracted to this negative electrode, which is the source of electrons. The sodium is combining to form that solid sodium, so where it's getting reduced at the negative cathode, we see a buildup on the electrodes. So that phrase, red cat gets fat, is still applying to the electrolytic cell. The cathode is still where we're going to build up atoms on it. So just to recap, cathode is where the electrons are sent to. This is where reduction is still occurring. However, we consider this the negative electrode. Anode is where electrons are drawn away from. This is where oxidation occurs. And unlike voltaic cells, this is our positive electrode. So electrons are forced to flow through the wire from the anode to the cathode. And so we can see that in terms of a power supply being present. Normally in voltaic cells, at least the ones that we work with and the diagrams we will work with, we don't have usually a salt bridge. We're also though forcing a chemical reaction, so this is always going to contain a power source to force the flow of electrons. Electrolysis can also be used to electroplate metals onto a surface. The material that is going to be plated, whether it's a piece of silverware or a piece of jewelry, is always going to be our cathode, so that we have a buildup of new material. The anode is always going to be made up of the metal that we want to use for plating. So here we have an electrolytic cell set up for electroplating. We're going to assign the silver bar, which is the metal to be plated, as the anode, the object to be plated as our cathode. We know anode is oxidation, cathode is reduction. We can then go ahead and assign our positive sign for our anode, negative sign for our cathode. We know that what's going to happen is that silver with a 0 oxidation number, we're going to strip the electron off of it, send it through the wire. That puts the silver ions in solution, which then are attracted to the electrons arriving at the spoon and recombining onto the spoon. So predicting the direction that electrons will flow would be from the anode over to the right where our cathode is currently located. We determined that our negative electrode was the spoon, the positive electrode was our silver bar. Reduction is occurring at the spoon, oxidation is occurring at the silver bar, and then we know reduction is at the cathode and oxidation is at the anode. Alright, so the big thing with these is just being able to recognize whatever the object is, instantly assign that as the cathode and reduction, and then whatever is the material to be plated, go ahead and immediately assign that as the anode. So we do need to be able to compare and contrast the two types of electrochemical cells that we've covered in this topic and 2 topics ago. Energy conversion is a difference between these. Voltaic takes a chemical spontaneous reaction and converts it to electrical. Electrolytic cell takes electrical energy and converts it to chemical energy by forcing that flow of electrons. We know that flow of electrons for a voltaic cell is spontaneous, happens on its own. Electrolytic, it's forced. The direction is a similarity between the two. Electrons are always going to flow from the anode to the cathode, so A to C. The reduction half cell always occurs in the cathode. Oxidation always occurs in the anode. Another similarity between the two. And then finally, one of the big differences that we need to be aware of is that our positive electrode is going to be the cathode in a voltaic cell, while it's the anode in an electrolytic cell. The negative electrode is our anode in a voltaic cell, cathode in our electrolytic cell. One thing with this setup is that we will have a voltmeter in the voltaic cell to record the cell voltage, and in an electrolytic cell, we have a power source. In the examples that we work with, we're also going to see that the voltaic cells tend to have the salt bridge, while our electrolytic cells that we work with do not have a salt bridge. Excuse me. Also, voltaic cells that we work with are usually going to be set up as two separate cells, and then an electrolytic cell will usually occur in one container, again with the examples that we use in our class. So a couple other things you might want to note there for the device setup that don't hold true throughout the chemistry world, but that will take place in our diagrams. All right, that's it. So you're all set. Make sure you look back over, especially look at the chart comparing the two cells. You might want to even go back further in your notes and review voltaic cells and being able to compare them to electrolytic cells on your own. All right, so you're all set. No summary, no quiz for this concept.